So welcome back to another episode of 12 Classes. It's going to be another one of those improvised sessions where I write on paper. But I'm talking about a physics class today. I'm actually talking about 3 different physics classes today, all combined into one video, and they're going to be about quantum mechanics and atomic physics. So let's get right into it. Now, at the beginning, I did say 3 classes, and that's not a mistake. There's 2 quantum mechanics classes that I studied, and there's 1 atomic physics class that I studied, and I'm sort of clumping them all together and just talking them as one big field of physics, because they sort of are. So I'm going to ignore atomic physics for a little while, and I'm going to focus on quantum mechanics first. So what is exactly quantum mechanics? What is it? Well, quantum mechanics is the study of really small things and the motions of really small things. So you might have seen my video on classical mechanics. Classical mechanics, you deal with, for example, particles moving, or you deal with bigger objects moving, maybe a ball, and you know that it follows things like F equals ma and, you know, all those stuff. But this turns out to not really work when you're talking about things on the smaller scale, right? So if you want to explain things on the smaller scale, things like the movement of an electron, for example, of how it moves and where it might be and stuff like that, you need quantum mechanics. Now, in quantum mechanics, you try to describe the motions of these objects, and you might have heard of a couple of things like in quantum mechanics already. So in quantum mechanics, there is the idea of something called a wave function. A wave function, well, is literally just a wave. So if I draw something like that, so this is what a wave function might be in space. So it turns out that every particle has got, well, these things called a wave function, usually denoted by psi, this symbol. And it basically, in theory, describes everything about our molecule or our atom or whatever the thing is we're trying to describe. The information about, for example, its position is all encoded within the wave function, but so is its speed, or more specifically in quantum mechanics, its momentum, things like that. But in quantum mechanics, well, having this wave function doesn't guarantee that you'll know exactly what the position of the particle is. And the reason is because quantum mechanics is non-deterministic. Non-deterministic in the sense that everything that you know, you can only know the probabilities of different things happening. So for example, the wave function will somehow encode the information about where the particle might be, but not tell you exactly where it is. So if you can see here, I can draw this sort of graph like that, and this basically tells you that, you know, particle is most likely to be here, but you might also find it here with less probability, or, you know, or even out here with even less probability, things like that. So you don't know exactly where the particles are, but you sort of can guess where they might be. And it's more probabilistic and it's not definite sort of thing. Same with its speed. You can't tell its speed directly, things like that. Now, the waves here, well, if you have an electron, well, of course, it might be moving. And the wave function will then also evolve over time, meaning that, you know, right now it's in this position, eventually it might be in another position. And the way that you describe how, you know, these particles or these wave functions evolve over time, because of course there'll be a function of time as well, how they evolve over time is described using something called the Schrodinger's equation, which looks something like this. I'm just copying this off somewhere online so that I don't get it wrong. But basically, this is what we call the Schrodinger's equation. It's probably the most important equation in quantum mechanics, or at least in, well, one of the interpretations of quantum mechanics that is most popularly studied or most introduced first. This equation basically describes how the waves moves over time, or waves changes itself over time. Because if we have an electron just moving along in classical mechanics, well, the wave will also have to maybe propagate along. So over time, the wave will, for example, maybe move over time or something like that, right? this equation basically describes it. And for a while in quantum mechanics, once you're introduced to this equation first, you study about, well, how this propagation or how the wave functions changes over time, how it does actually happen. So these symbols looks complicated in quantum mechanics, but basically, it basically just says like this is, the factor of how it changes over time. This is something called the energy operator, or the Hamiltonian. The actual name is the Hamiltonian operator. Also, sort of like tells you, it's like an energy operator sort of thing. I don't really want to go into details on how to describe it, but for a while you learn about how you might go about solving the Schrodinger's equations for some of the cases, and that's what I did for a lot of quantum mechanics 1. So this case is a case of a free electron, when the electron just is allowed to move freely in space. But then there's also other cases of like Schrodinger's equations that you look at as well. So one example is when you have something called an infinite square well, usually drawn like this, and it is when this area and this area is out of reach for a particle, and the particle is only allowed to stay within this confined space. And the wave function might look something like that, or it might look something like that, things like that. And you talk about other potentials as well. There is, for example, what we call the harmonic oscillator, when the potential looks like a quadratic function. The potential basically is sort of like similar to the potential energy in classical mechanics, but in this case it is for the atom. And then again, those will have different wave functions, which I actually can't remember how they look like exactly, things like that. Then you talk about other potentials as well. For example, what if you have a step function, or what if you have a finite square well, where the electrons will have low potential with this area, but then can still go to these area because it's not infinite. Or what if you have a delta function, where you have one giant spike right in the middle, things like that. So you spend a lot of time in quantum mechanics 1 just mostly looking at the mathematics, and mostly, as you can see here, in many of these cases, look at particles in 1 dimension, then asking some of the more easier questions, like what will the wave functions look like, and mainly just get into the fields of quantum mechanics and learning about some of the more mathematical properties, like what are the properties of the propagations of these particles, or the fact that if you have this wave function and this wave function being possible wave functions for the particles, you can combine them together, and then you can create another wave function, which will still be a solution to this. That's called the superposition principle. And like the actual the electron might have like some initial state that it is in. If we know the initial state, then using superposition principle, we can find how that initial state will propagate over time, things like that. And it's a very interesting subject, but it's also very mathematically heavy. But again, as I've mentioned, this is more in the sorry about that, in the one-dimensional case, and that's what you mainly do in quantum mechanics 1. When you get to quantum mechanics 2, this is where things really step up a notch, because now you start talking about quantum mechanics in 3 dimensions, and that's where it gets really hard. But at least it also gets even more realistic. So one very big example of this is the case of an atom, or a hydrogen atom in this case. So hydrogen atom, you have a proton in the middle, and you have an electron circulating around it. The electron might be anywhere around this atom, and that there must be interaction between these 2 particles, and the interaction is due to electrostatic force, and that there is a potential for that. The potential energy turns out to be in the form of K Q, or not actually Q, the charge of the electron is E, so it would be minus KE squared over R. The potential is basically proportional to 1 over R, or 1 over that distance. And you ask, for this case of potential, what does the energy of the hydrogen atom look like? Or more specifically, what are the wave functions of these atoms? And well, there are very complicated maths you can do to solve it, because, well, Schrodinger's equation is there, and this is basically the entire thing about quantum mechanics. It's almost like the second law of like quantum mechanics, in the sense that it's really fundamental and you sort of use it to calculate everything. I mean, it's not really like force equivalent or anything like that, but basically you can use that same equation to try to solve this case as well. And you know, you end up with wave functions that looks maybe, for example, like you end up with many wave functions. Wave function that looks like a circle, wave function that looks like this shape, or one which looks like a ring sort of thing, sort of like that. You might have seen some of these before as the atomic orbitals, like the 1s, 2s, 2p, all those different stuff. And precisely, that is precisely where they come from. They come from you solving the Schrodinger's equations to get to these different cases. But one other thing that is interesting that I haven't actually mentioned is about the energies of these states. Because these states will also have different energy levels. So for example, the lowest energy level that the electron can have, the lowest state, or the first wave function will, you know, have some energy level, maybe called the first energy level, or n equals to 1. But then there will be other energy levels as well, n equals to 2, n equals to 3, and so on, upwards. But the most important thing is that, unlike in classical mechanics, these energy levels, which I will have like these energy levels with increasing energies, these energy levels end up being discrete or being quantized. In other words, the electrons can have this energy level, or the electrons can have this energy level, but the electrons cannot have this energy level right in the middle. It cannot do that. It can only exist between, well, very discrete points of energy. And that's the whole idea of quantum mechanics, that the energy is quantized. In other words, they are in different, well, very fixed positions. And if we have an electron that wants to change its wave function and go there, then it needs to absorb some photon and get excited. But the photons has to be exactly, you know, like this energy gap. Otherwise, it will not be absorbed and then it can't jump. Things like that. And, you know, basically these are the whole things about quantum mechanics. Learning about the wave functions and then learning about what these energy levels, they might look like. Things like that. But then there's other things about quantum mechanics too, rather than just solving the Schrodinger's equations, because it turns out that, you know, in these cases that you've seen, they're relatively easy to solve. There are analytical solutions you can use to solve them. In other words, you can exactly write this equals to something, right? Like in exact terms. So even a function of x as well, function of position and time. But for many other cases, we cannot do that. And so we need to include, for example, we need to learn about correction terms and like how you can approximate different solutions. And then we get into things, many other approximation techniques, things like the perturbation theory or the variational method or WKB methods, all those different things. And you can use those to like have even more accurate models of different things. So now, for example, the energy levels, in truth, if you actually like work out the energy levels of an electron, these are not it. Eventually you learn that, you know, you can make approximations, and through those approximations you learn that the energy actually splits. There's splittings of these energy, and so actually these one lines corresponds to many more smaller fine lines, and this is what we call the fine structure of the hydrogen atom. But they are still discrete energy levels, just not, you know, simply n equals 1, n equals 2, n equals 3. There must be, for example, other energy levels depending on other things, like, for example, the spin of the electron, or, you know, there's I can't really remember the other effects and things like that. And so quantum mechanics too still describes, like, still looks at the mathematics of like the system and then tries to describe these sorts of things. And that leaves one more thing that I haven't described, and that is atomic physics. And atomic physics tries to even go into something even deeper, because atomic physics describes, well, talks about atoms, right? But we don't just talk about, for example, hydrogen atoms, we talk about more complicated atoms as well. So for example, a helium atom, where you have a helium nucleus looking like that, and you have 2 electrons whizzing about instead. And the fact that you have two electrons makes it a lot more complicated, because now the potential is not this simple term, but the potential depends on, well, the atom interacting with both of the electrons, but then also the electrons interacting with each other as well. Things like that. And so how do you write out a wave function for the two electrons? For the electrons, how would they look like? Things like that. Well, it's really hard to solve. In this case now, you have to make some approximations. And more importantly, if you have these wave functions for the electrons, what will their energy levels look like now for these cases? And you can like try to generalize it for even more complicated atoms. So for example, even the next one up, lithium, you have a nucleus, you have two electrons, which for the purpose of this video, you can assume as like this whole thing is one nucleus, because these two electrons tend to be close together. You can look at the electrons in the outside, what wave functions it might have, because lithium has got 3 electrons. But then you also look at other things. So for example, like if you have an atom with a wave function, that looks like an egg, but that's a wave function. And you have like an electric field running through it. How will that affect the energy levels of the atom? There will be, the splitting will get even bigger. I think that's called the Zeeman effect or something like that. And like this changes like how the electrons behave even more. And there are different things like, for actually, these energy levels aren't discrete. They're actually, you can sort of have it like a little sort of distribution. So like maybe it can be off by a little bit, things like that. Or like, how do lasers work? I think one big thing about atomic physics is also about the applications of, you know, quantum mechanics and principles in atomic physics, or like these things to other branches of physics. So for example, if you have two states, you can have them oscillating between the two states, right? And like, for example, it might oscillate between the two states, and the oscillations can take a certain amount of time, and that certain amount of time can be, you know, can be calculated. And in some cases, the oscillations between the two states can be calculated so precisely that you can use it to define time. So that's the idea of atomic clocks, where you have two energy states and you have the electron oscillating between the two energy states in a fixed amount of time. And then you can use that to define the second by saying the second is equal to the amount of time for the electron to oscillate this many times, things like that. Or the fact that, you know, you have these wave particles, and these wave particles, you know, doesn't just have one fixed state, but they can be a combination of state or a superposition of different states, means that you can have an atom, you can store an atom, and they will have, you know, some complicated wave function or some complicated states, and then you can use that fact to store information within these atoms. And by doing so, you can use it to do different computations, and that's where you get things like quantum computing. And quantum computing is major because it turns out that you can do very complicated mathematics with it. And well, I mean, or at least in theory you can, until someone actually invents like the actual computer architecture to do these things. But in theory, it allows you to do some things a lot quicker, things like breaking cryptography, which will be a big problem if it actually happens. Like, atomic physics is a really fascinating subject, and I think it's probably the hardest subject I have studied in it, well, amongst any class at all, across every single field that I've studied. If any one of you see my vlog on my second channel where I spent a term abroad, I actually took atomic physics there, and it was really complicated. And honestly, I wasn't really into it, mainly because of like how much maths there were and how little intuition there was. It was not like that, where, you know, you can sort of imagine how things would move. It's a lot more about, you know, waves moving, and you just dive into the mathematics and you don't know where you get out of it. But it's still a very fascinating subject because, you know, it allows you to get even closer to like reality. And even for something so abstract like this, there are still actual uses for it, and I think that's really cool. It's just not something that I'm really into, and maybe that's a bit of a bummer to hear, but it's still something really fun. And honestly, I forgot most of it, and that might be why, like, hopefully I didn't get too many things wrong. But yeah, basically that's it. That is, well, quantum mechanics and atomic physics, or basically the very, bare bones, what they might sort of are. I rambled a bit. I didn't realize it was almost 20 minutes already. But anyways, thank you very much for watching today's episode of 12 Classes, and I'll see you guys again tomorrow when I talk about a computer science class that is probably really popular nowadays.